Roughly 80% of the total mass of our universe is made up of something called
dark matter.
Dark matter.
Dark matter.
But what exactly is dark matter? Our universe started around 13.8 billion years ago and has been expanding ever since. This expansion is the spreading of the space-time structure itself and not the actual moving away of the celestial bodies. Hold on, but galaxies are themselves vast structures, the largest being 5.5 million light years in diameter. Which begs the question, why aren't these galaxies expanding and withering away after some time? Is there some mysterious force that is binding these vast galaxies together? To our surprise, there is an invisible force doing this, and we call it dark matter. Every second, millions to trillions of particles of dark matter flow through your body without even a trace. But how do we know dark matter exists? Or how does it work? Let's find out. My name is Siddharth, and you're watching The World of Science. There are many types of galaxies, the most common being the spiral galaxy, like our own Milky Way galaxy. The earliest evidence of the invisible force binding galaxies together came from the study of spiral galaxies itself. According to standard physics, stars at the edge of a spinning spiral galaxy should travel at much slower velocity than the ones at the galactic center where the galaxy's visible matter is concentrated. However, observations show that the stars orbit at more or less the same speed irrespective of where they are in the galactic disk. In 1933, Swiss astrophysicist Fritz Zwicky studied a group of galaxies called the Coma cluster. He calculated the mass of a galaxy in two ways. Firstly, based on the motion of the galaxy near the edge, and secondly, based on the luminosity of the galaxies and stars visible. Okay, let's first understand some basics of astronomical calculations. In astronomical measurements, various parameters are related, such as according to the Stefan-Boltzmann law, the luminosity of a star is directly proportional to its mass and also to the fourth power of its temperature. Now, you may ask, how do we find luminosity? It can be measured by calculating the light emitted from a particular region and is dependent upon distance and scale factors. Okay, so now we have one way to calculate the mass. The other way is to use the motion of the stars. Stars revolve around the galactic center and their velocity is dependent upon the distance from the center. According to classical mechanics, as the distance from the center increases, their orbital velocity decreases. By equating the kinetic energy to the gravitational potential energy, we can calculate the mass of the stars. Now, Zwicky was a smart guy because he performed both the calculations. He calculated the mass based on the motion of the bodies on the outer edge of the galaxies and also on the basis of the luminosities of the visible galaxies and stars. Now, interestingly, the numbers did not match. The mass calculated based on the values of brightness was much lower than the mass calculated based on velocity. These values can be plotted on a graph called the galaxy rotation curve. On the x-axis, we have the distance of the star from the galactic center, and on the y-axis, we have its orbital velocity. Now, from the visible analysis, the velocity curve should show a decreasing trend. Because as mentioned earlier, with an increase of the distance from the galactic center, the orbital velocity decreases. But then here comes a plot twist. The velocity curve showed rising values. This is strange because the orbital velocity of planets in planetary systems and the orbital velocity of moons orbiting planets should decrease with the increase in distance, according to the famous Kepler's third law that we have all studied. For example, Mercury takes only 88 days to make one revolution around the Sun. As for our planet Earth, it takes 365 days, and the planet Saturn takes a whopping 10,759 days to make one revolution around the Sun. So now, Zwicky's analysis showed a discrepancy in the calculation process. But how is that even possible? If Kepler's laws are correct, then the only way to resolve this discrepancy is to conclude that the mass distribution in the galaxy is not similar to that of the solar system. So Zwicky proposed that there is some invisible matter that adds up to the mass of the galaxies in the outer region, which he had not included in his calculations. Zwicky found out that individual galaxies within the cluster were moving so fast that they would escape if they were held together only by the gravity of its visible mass. Since the cluster didn't show any sign of flying apart, it must contain an abundance of dark matter, about 10 times more than visible matter, to obviously bind it together. Zwicky's conclusion was correct, but his colleagues were a little skeptical. Then came Vera Rubin, an American astronomer who realized that she had found compelling evidence for Zwicky's dark matter. She found out that most of the mass of the universe is hidden from our view. She teamed up with Kent Ford, an astronomer who had developed an extremely sensitive spectrometer, and went on to study some 60 spiral galaxies and always found the same thing. What you see in a spiral galaxy is not what you get. Her calculations showed that the galaxies must contain about 10 times as much dark mass as can be accounted for by the visible stars. In short, 90% of the mass of the galaxies, and therefore the observable universe, is invisible and unidentifiable. Dark matter holds the galaxies together. Unlike normal matter, dark matter does not interact with electromagnetic force, which also means that dark matter does not absorb, reflect, or emit light, making it extremely difficult to spot. Researchers have been able to infer the existence of dark matter only because of the gravitational effect it has on visible matter. Dark matter accounts for 26.8% of the total matter in our universe, while 68.2% is that of dark energy, which acts as a cosmological constant, exerting a repulsive force that pushes the universe outward. The remaining 5% is all of visible matter in our universe, and this fact alone is enough to show the vastness of our universe and its unknown nature. The theory of dark matter is one of the most important unsolved problems in physics. Various proposals such as self-interacting dark matter or some yet-to-be-discovered subatomic particles such as axions and weakly interacting massive particles, WIMPs, have been put forward to solve the mystery of dark matter. WIMPs in particular are widely studied in the field of dark matter cosmology. According to this theory, dark matter is composed of particles with a mass close to 10 to 100 times the mass of protons. These particles interact with normal matter particles only through weak nuclear forces and gravitational forces. They do not interact with matter electromagnetically and thus cannot be directly detected. Their gravitational pull binds them with matter in galaxies. Due to their large mass, WIMPs have low velocity, allowing them to clump together smoothly and form large structures. And their normal temperature is very close to the ambient temperature of the universe, giving them the name cold dark matter. Although WIMPs possess the necessary characteristics to be considered dark matter particles, they haven't been observed or discovered yet. The high mass of WIMPs means they can only be observed during collisions in the Large Hadron Collider. Unfortunately, apart from the Higgs boson, no significant particles have been observed in the LHC. But there are plans to increase the LHC's capacity in the near future, and researchers are hoping for new discoveries through these efforts. Some other potential particle candidates for dark matter include neutralinos. These are hypothetical particles which are slower and heavier than neutrinos. Neutrinos are particles that do not make up regular matter. Neutrinos continuously stream from the sun, but they rarely interact with regular matter and can easily pass through Earth. Apart from the three already known types of neutrinos, there's a speculated fourth type of neutrino called the sterile neutrino, which is the proposed candidate for dark matter particle. And this sterile neutrino would interact with regular matter through gravity. Dark matter reminds us that our universe is full of wonders waiting to be discovered. So that sums it up about dark matter. But do you know about dark energy? Because honestly, it's even more mysterious. You can know more about dark energy by clicking here or through the link in our description. If you like this video, please share it with your friends and do check out the other videos on our channel. Make sure you subscribe to the World of Science. Until next time, stay scientific.